Hi everyone, this is Anagh and he's Vignesh. And we're going to tell you about a project called Just-in-Time Sign Translation, my bad. So, why are we doing this? And there's a reason. So, Vignesh had a friend, and that friend's parents actually came to town, came to Pittsburgh, and when they got to the airport, they were left stranded because they were unable to figure out the signs. They were unable to follow what was written up there, which way is arrival, which way is customs. They were unable to see that. So his friend actually was on the phone for 2 hours with them, explaining to them constantly at each turn of the way, at every turn of the way, where to go, what to do, what not to do. And that was a very, very tough and troubling experience. Vignesh will attest to that. So what we thought, okay, can we remove this obstacle from our lives? And we thought, okay, yes, we can. Why not use a portable device, like a glass or like a phone, and try to use that for object recognition or like to take that one step further, even translation of text on objects like signs, other boards, restaurants, hotels, anywhere where you see signs. How about if you're able to translate them and get to know what it means immediately? So, thinking about this aspect, we thought, how do we go about constructing a system for this? And we came up with 4 main areas where we can concentrate upon. So, the first one where we focus on is the communication aspect. So, once you have a wearable device like a phone or like a Fitbit that Vignesh is wearing, or even like a glass, you want to take some picture from it, and then you want to send it to a cloudlet for actually computing what is in there. So this communication aspect from the wearable device to the cloudlet is taken care of by Gabriel. Gabriel, as we all know, is a system developed here at CMU for actually communicating between devices and cloudlets. And it actually provides us a unique abstraction for assuming that the entire cloudlet is just a platform which will allow us to do independent functions. So it's kind of a platform as a service layer. So once we have our captured image from our device onto the cloudlet, what do we do with that? We want to figure out, is there something interesting in that image? And to figure that out, we want to see, is there any text in that? So we want to detect, hey, is there text on that image? And the way we do that is actually using ER algorithms, that is the extremal region algorithm. And Vignesh is going to talk about it in more detail, but the primary reason why we use it is it allows for color distinct recognition too. Basically what that means is if you have a green board and you have text on it with dark green, other algorithms may not recognize it due to their grayscale nature. So they'll just scan over it and say, hey, there's nothing over here. But ER is going to come back to you and say, hey, I found this text and you might be interested in this. So that's one big win for us, and we go with ER for the text detection part. So okay, once you have an image, you found, okay, there might be something of interest, and you have some sort of bounding boxes given to you by the ER algorithm. What do you want to do next? You want to recognize what is in that bounding box. And that recognition is taken care of in the text recognition aspect, which is the third component of our system. We achieve that by using OCR, that is optical character recognition, done via Tesseract. And Tesseract, you give it some input, it's going to spit out, okay, this is the text that I found in that particular input range. So Tesseract is actually very easy to plug into the system. And if you notice in the architecture that we have over here, you have a device communicating with a cloudlet, and the cloudlet contains one event bus. This event bus is actually component number 1, Gabriel, which takes care of the communication protocol. And then when you see, you have multiple Tesseract boxes. We like to call those boxes as engines. So you have multiple Tesseract engines running on one cloudlet. So essentially, it allows us to scale better too. So if you have large amounts of text, you can actually distribute it. And once Tesseract actually comes back and gives you the text that, okay, in the image that you gave me, I found in this region a particular word. And this is what that word is. The last thing that remains is to just convert that word into the language of your choice. Over here, we'll be focusing on Spanish, So we want to do essentially text translation from English to Spanish. And again, we use another tool called Apertium to help us achieve that. It takes the input of the previous stage, that is the Tesseract stage, a word in English, and then it converts it to the Spanish translation of that word. And to put it all again together, we have the device communicating via Wi-Fi to a cloudlet. The cloudlet contains a central coordination server, which takes care of the bus, and the bus has many engines attached to it. You can see there are multiple Tesseract engines. We even have the language translator engine, which is essentially the fourth component in our system. And once you actually put all of these together, you can actually see it's quite a cohesive system. And now, one thing that I would like to point out here is that the beauty of Gabriel is that it allows you to do computation without actually taking care of the rate at which you have data coming in. So Gabriel has this concept of token level filtering, two-level token filtering, and it essentially does a great job at rate limiting. And then we don't need to do a lot of computation involved. We just simply get the image from the device and we push it off to our Tesseract engines on the event buses. Now I'll hand it over to Vignesh, who will get you excited about the results that we got.
So thank you, Anagh. Is my voice audible? Yep. Yeah. So you can argue saying that, hey, this is very similar to what a Google Translate would do. You take an image, you find the language in it, and you actually translate the language. So what is it different what we are trying to do here? So one thing what we are trying to do here is we are trying to evaluate if you actually put this particular solution on, say, a cloud which is deployed somewhere very far from you, versus how does this solution work when you're actually putting it on a cloudlet. So the primary difference is cloudlet is going to be a computer or a server which is going to be on the first edge of your computing scale. So what happens is we wanted to see how this would actually play a very big role in having such a streaming kind of an event. When we look at the results, we were actually amazed to see that the cloudlet solution was actually beating almost all of the solutions which were there, which we actually compared. So what we tried to do was we tried to deploy the same service on different availability zones in the world, ranging from regions in the US, both east and west, some regions in Europe, and some regions in Asia too, to see how latency would be a very big factor when we're actually putting different solutions there. So what we see is, let me actually deep dive into this particular image here, and let me give some clarity about how to kind of read this image here. So you can ask, what is this fancy image what we have here? So what we're trying to do is, at each test, we are trying to send around 65 frames to the backend server. And what would happen here is, we would try to measure the latency for each of this frame to see how would this work. Since all of these guys are going to send the same particular frames, we would know that the ratings here is going to be very similar, and you can somehow compare apples to apples here. That's the whole point of this. So what we saw here is, if you see the white line, which is indicated here, is actually what you can get from a cloudlet. And just with any possible line here, you can obviously see that the white line is below any line here. And that kind of gives a very big heuristic that cloudlet beats all solutions. I'll deep dive into some of the solutions here much further to kind of get an understanding of what is there. So this line here, what we see is the Amazon West line, which was actually deployed in North California. We see that they had an average rate of around 650 milliseconds. And sometimes the highest range was reaching around 1,250 milliseconds, which is around 1 second to get back a frame, and more than a second to get back a frame. We see that slowly when you actually are moving away from where you are, latency starts to play an effect, and this is a problem when we have such a streaming kind of an application. When we actually did the same thing with Europe, we were actually amazed to see that the results were actually comparable to what Amazon West gives. This is a kind of a contradiction, because you see the distance between, this was actually deployed in Frankfurt. And what the distance between Frankfurt versus Pittsburgh to North California was almost a double. Frankfurt is around 4,000 miles, whereas North California is around 2,000 miles. But this guy gave almost a very similar result. This kind of got us worrying, thinking about what can be the possible reasons. That is a story of a different day. But possible reasons could be that you have a transatlantic cable going on, and that might actually be a primary factor in which can reduce latency. Another thing is the number of traffic which is getting into the Amazon West might be significantly high than what it can be for Europe, and that might be a reason why you can also see a decrease in latency. But the actual factor has to be evaluated to see why this was the case. The furthest line here, which is the whitish kind of line, actually is what we see for Asia. We kind of we deployed a box in Mumbai where we saw significant increase in the the latency and the return times. This particular call here, or even this particular call here, was close to 1.9 seconds, which means in 2 seconds you're just getting back one frame. And since this is a streaming kind of an application, this is not at all tolerable for a user because he would have a very poor user experience. So you see that here, at least the effect of latency is seen to its max, and we see that this is very negative. Circling back, let's go to the first line here. So we see that the Amazon East line here, which is very comparable to Cloudlets. Amazon East obviously is in North Virginia, very close to where we are in Pittsburgh. You see that here, this would actually give a very good comparison of how you could make sure that Cloudlet beats other solutions here. The distance is very low. You would actually, there is a thing which we recently learned was CMU has a dedicated line fiber which runs to Amazon East to boost their connectivity speed and broadband for CMU. So what this would actually affect is you would actually see lower times than what a usual customer would see. Even with those lower values, we see that Cloudlet was actually beating what Amazon East would give. So this is a very clear indication that Cloudlets is actually a very good scenario or a very good use case here for this particular application. So getting to the lessons learned, I would at least get back to this particular point saying that Cloudlets was consistently 20% or 19% faster than what Amazon East used to give. And this is a very good kind of a takeaway for us. We were introduced to this idea of Cloudlets being fast on the since it's in the first edge. But when we actually conducted these experiments, we found out that it's actually true. And it was kind of satisfying to see that what we were taught, it was actually what we actually see in the results as well. The lessons learned. What we actually see is the technologies actually play a very big role in which you choose a solution. But the most important part here is technology alone is not the solution. Technology must be bent to a way in which it can actually meet your solution rather than you going and stretching out to technology. We learned this at least the hard way because we initially wanted to just finish our application with Tesseract, which is just an OCR engine given by Google. But what happened is our scenario is much different than what Tesseract would do. Tesseract, given a PDF file, it would actually find out different regions of text there on the page, and it would do a very good job of finding text in that. But when you give a very noisy image which has a lot of background noise, for instance, take this image here which says wrong way. Here, you see that you have a lot of noise other than the text here. Tesseract would do a very bad job in finding out what the text is here. So we kind of identified that we have to do something really fundamental here to make sure that we can get the parts of interest out of the image so that Tesseract can just do those parts and get out what it's actually built for. So that's where we found out that pre-processing is very important. One of the key learnings we had. Another key learning which we had was actually the ER algorithm was a very good fit for what we actually did. This is because, as it's indicated here, when you're actually viewing things from a different angle, there might be a different point of views, there might be blurring of the whole image, and there can even be parallax of views there. So our solution must be fair enough to make sure that it can find out these texts there, and it can do a good job in identifying text. So when we actually put ER algorithm to the test, we found out that this actually met whatever we needed, and we were actually happy that this was one of the good decisions we made. Uh, to circle back, ER algorithm was actually found out in the OpenCV repo, where they actually had a lot of models developed there, and we kind of saw that this is also beneficial for us since they had their trained models. This would make sure that it would become very fast for us to also like do our application there. Uh, Finally, when we are touching upon ER algorithm, we saw that the way in which at least ER algorithm works is it tries to find out text in different channels. So how it does is it tries to find out what are the different channels possible in an image, and in those particular channels, for instance, if you take RGB, which is nothing but red, green, and blue, what it tries to do is it tries to find out text within these channels, and after it finds out text within these channels, it'll probably say, hey, this is a text here. Probably this is of interest for the OCR here. So this is actually this was very effective because it made sure that you don't miss out on a lot. But on the negative side of this, what we see is since it's calculating a lot of things, this might be a very big problem for us because we are on a very tight schedule with time and latency here, and this might add to the latency here, and it might add to the processing time here. So we found out that there must be this balance between how much of false negatives or false positives you want in the application versus how many channels must be considered for your latency. So that was one of the most important learnings we had. That probably concludes what I have here, and these were one of like few of the most important references which we actually followed upon or we used when we were actually building the application.
As you can see, this is a very noisy image that you have in front of you, and it has a text speed and limit. 25 is fairly constant in almost all the languages, so we don't focus on translating numbers right now, but we are focusing on the words. You can see there's lots of noise on the right of the text and to the left. And we have our application over here, the Gabriel client. Gabriel has helped us a lot. This is what the Gabriel client is doing. It's going to communicate, and I am going to switch it on right now. And I'm going to hold it over the speed limit. Can you redo this? This does tend to crash a bit, but we will show you a working demo shortly. As you can see, it is recognizing the word.
So you can say that there are flashes of text which
There are flashes of text. The word is getting recognized, and you can see that once it recognizes the word, it tries to actively blur out the arena. And once it blurs it out, it actually rewrites the translation, say speed in this case, translates to velocidad in Spanish. And that is what it writes out on here. We can try to restart it and see it again in effect. And it tries to translate both the upper word and the lower word independently of each other. You can see it flashing over there, and we can show in continuous motion it being removed and another object being introduced. And the system will attempt to translate this. And as you can see, it is still translating. So we don't just capture an image and then send it for processing. We are processing the streaming video in real time over here. And we aim to get a real-time translation by blurring out the irrelevant edges. We can try to restart this and redo this one.
send it there, but it's now there.
And we can try to show you how it's happening on the back end over here. Once you actually hold up the phone over an image, this is the back end of the cloudlet that's actually here. And the cloudlet is actually recognizing frame by frame each thing that it actually saw in the image. And if you can zoom in over here, you can see that the tesseract text that it recognized from this image that we have over here, you can see it says floodway over here. And it actually recognized the tesseract text as floodway over here.
With some mistakes there. And that's why.
There are, obviously, this is not perfect. There are other noises that get added, so it does tend to get a bit cluttered with other variables. But again, like as you see over here, this did recognize floodway correctly, but it inserted unnecessary spaces. And then the text that it actually extracted, it said that, okay, it's just way. And then it tried to translate the text to Manera, which is a close enough translation. I'm not the authority on Spanish, so I won't say that, but it is attempting to translate it. And similarly, we can see in other cases also, as we can see, we have another image of a stop sign here, which it actually translated to Paron over here. And we just have the stop sign in like color and grayscale to show that our thing will work. We can try it out. Or we can actually see a demo that we do have recorded. Uh, this is the screen at start, and then we click start. This is showing you again that the right side is the one that's actually the live video that your camera is capturing, and the left side is the one that it's getting translated. It may be too minuscule to see right now, but that is what's actually flashing on here. It's translating Floodway to Monero over here as we saw over there. And stop is going to get translated to Paron over here, but the video will cut out before that. And this will keep looping. And that's what we had from our side. In conclusion, Gabriel is a very good accompaniment to the Cloudlet, and thanks to all the Gabriel team at CMU. Thank you.